So we have seen how to find out the confidence interval when your sigma square or the variance is known to us. So the formula for that we know. Now, if you look at that interval, or you consider any interval for a parameter theta, then if it is a two-sided interval, then in that case the length of the interval would be just be u minus L, the upper limit minus this lower one, upper bound minus the lower bound. It's easy. Now suppose you are interested to obtain confidence interval that are as narrow as possible, because we do not want it to be very wide. The reason for that is, suppose you consider this simple example, you make two statements. First, you say that I am 90% confident that the average selling price of the smartphone is between 20,000 to 28,000. Now, and the friend of yours make a statement that I am 90% confident that the average selling price of the smartphone is between 23,000 to 25,000. Then which one is a better option? The one in which you have lesser range, because in that case it shows that you are more confident that this is going to happen with 90% confidence. So in this case you see that the second option is better because you are more confident. This is a wider range. So based on this, if you consider the z interval, then length of the z interval will be what? So you can see that u in this case would be x bar plus z alpha by 2 sigma by root n minus of this quantity. So here sample mean would cancel out from these two terms in the square bracket, and you will be left with twice z alpha by 2 sigma by root n. So what you see over here is that length of the interval in case of z interval basically depends upon three factors. What are those factors? It depends upon your sample size, it depends upon your standard deviation, and it also depends upon the confidence level that we have described through z alpha by 2. Okay, so these are the three quantities. Now how is it depending on them? We are saying that we want length to be less, right? We don't want such wider intervals so that the interpretation becomes vague. Now here if you see that n over here is in the denominator, so it means that if I increase the sample size, then the length would decrease. And that is correct also, because we always want to take that the sample size should be more, because here it is intuitively correct also, because we want the sample size to be large. So if you are taking samples of larger size, then your length would decrease. That is the first thing. The second thing is your standard deviation. So that is not in our control. So yeah, if it decreases, the length would decrease. And the third factor is your confidence level. So let us interpret what it is, and then we will come back to this slide. So length, basically we have seen that length of the z interval is twice z alpha by 2 sigma by root n. So we have seen that if n decreases, then the length would decrease. If sigma decreases, then again the length would decrease. Now what about this z alpha by 2? So it means if this also decreases basically, then this length will also decrease. So let us see what are these common values. So see, when I have I'm 90% confidence, if I use this confidence level, then the value of z alpha by 2 basically in this case, okay, it comes out as 1.645. So 90% means that 1 minus alpha is 90%. So alpha you can calculate from there, and you take alpha by 2 and you look at the standard normal table. So this value comes out as 1.645. At 95%, as I told earlier, it is 1.96, and at 99% it is around 2.58. Basically, if you see, if I am decreasing the confidence level, this is basically increasing, right? Z alpha by 2 is increasing. So I want to decrease z alpha by 2. It means I need to consider 90% or maybe 95% as opposed to 99%. But also, if you remember initially that we said that if I am more confident about certain concept or certain thing, it would make more impact, right? If I'm saying I'm 95% confident, then it would be better than saying I'm 90% confident about that thing. So although this value 1.645 is less and it would give the length of the interval would decrease, but we also know that it would be very less if I compare, it would be lesser than that of if I take 1.96, that is 95% confidence interval. So you can say that the width of the interval should be less, but we do not want it to be so less that it does not make any impact, and it should not be as wide, because if you take 99%, the length of the interval would become wide, but it would also not be giving you the correct answer. So just taking extra value would not be fine. So instead of that, we take 95% as the most common value, because in that case we do not sacrifice either the confidence level, because 95% is a good confidence level also, and the length of the interval would also not be sacrificed in that, because it is 1.96, which is between 1.645 and 2.58. So that is why you see that in most of the problems that you tackle, we always consider 95% confidence interval, and even if it is not specifically mentioned that this is your confidence interval, then also we take it as 95%. So you can simply take 95% and then move ahead. Now further, if we look at this, x bar plus minus z alpha by 2 sigma by root n. This is entire thing is your confidence interval estimate. Okay. Now what is this? This x bar, this is just your point estimate in this case, right? And this is the quantity that we are adding or subtracting to it. So this is basically referred to as the margin of error, because this much margin of error can be given that, okay, it is going to be lying between these two endpoints, so we can be negligent of these two. We are giving this much width for that interval. So this is the margin of error, and that is what we denote as E. So let me just show you in the slide. So here you can see that this is what I explained to you, and that is why we say that 95% is the most commonly used confidence level. So based on the formula of Z interval, as I said, x bar is the point estimate. This entire thing is an interval estimate for mu. Sigma by root n is the standard error of the mean, because x bar follows normal distribution with mean mu. Standard deviation basically sigma by root n. So sigma by root n is the standard error. And finally, z alpha by 2 sigma by root n is the margin of error that we denote by E. And now if you look at the width of the interval from the previous slide, so it came out as twice of this margin of error, because it was twice z alpha by 2 sigma by root n. I could just quickly show it to you. So it is this after 2, this entire part is your margin of error. So length is basically, or you can say width of the interval is basically twice of the margin of error. So if I have to calculate the margin of error, it is basically the width divided by 2. Now, another important thing based on this is how to determine the sample size. In order to determine the sample size, you have this equation that margin of error is this. Based on this, if you solve for n, what you get is this, because n would go to the left hand side, e would come in the denominator, and you square all the terms. Now, what is happening over here? Here we are taking z alpha by 2 whole square, e, and sigma square. So here we know, if you know these three values, then you can simply substitute it and you can find the sample size that is required for any given problem. So in that case, what happens over here is that sigma is often not known to us, right? Population standard deviation, that is not known to us. So we can use an approximate for that. And that approximation arises from basically your empirical rule. So if you can recall, in I think the second or the third week, we studied about the empirical rule, the standard rule of thumb, which says that 95% of the observations would lie between mu plus minus 2 sigma. And then we go to 99.7 for mu plus minus 3 sigma, likewise. So here, if we consider the empirical rule, then it says that 95% of the measurements lie in this interval. So let me just quickly tell you. So the empirical rule says that mu plus minus 2 sigma, in between mu plus 2 sigma, 95% of the observations would lie. So if I consider the length of the interval, so the length of the interval in this case, or if I just consider, say it as the range, so it is what in this case? It is mu plus 2 sigma minus mu minus 2 sigma. So that would be basically, sorry, this would be plus because it is mu. So it is mu minus 2 sigma. Sorry, mu would cancel out and you would be left with 4 sigma. So the range comes out as 4 sigma. So if I have to approximate sigma, so what I can do is that I could consider the range of observations given in your data. So sigma can be approximately range divided by 4. So you would be given the range in your data. Based on that, you can divide it by 4 and consider that for sigma, and you can simply substitute in the formula for your sample size. Because in sample size, you would have z alpha by 2, this value would be known to you, and then sigma you will approximate from here, and then e square would be given to you. Now the point comes basically that why are we considering only 95% confidence, 95% over here? Why don't I just consider, I can also consider mu plus minus 3 sigma, so that in that case 99.7% observations would be in between these two endpoints. If I do that, then the range in this case, or the length or the width of the interval, would be mu plus 3 sigma minus mu minus 3 sigma. That basically gives you 6 sigma. Now if I have to find the approximate value for your sigma, so that would be basically range divided by 6. Here, if you compare this one and this value, so what we are doing basically, here we are dividing by 6, and in this case we are dividing by 4. So basically, if I consider the second one, that is if I divide by 6, then this sigma would be a lesser quantity. It would be less than what you have obtained over here. If I take sigma less, then the sample size would also be less, because here it is directly proportional, right? So if sigma is less, then sample size would be also less. But that won't be correct, because we usually want the sample size to be more so that you have the correct precision. And in statistics also, we tend to overestimate the parameters as compared to underestimation. So that is why we consider range divided by 4 instead of considering range divided by 6. Okay, so the approximate value that you calculate for sigma, you have the range, you just divide it by 4 and you will have the answer to that. So let us consider an example for that. So you can see that same thing I have written over here. To approximate sigma, we use the empirical rule, that is 95% of the measurements lie in the interval mu plus minus 2 sigma, and divide the range. The range came out as 4 sigma, you divide it by 4. Okay, so then you can get sigma basically. So this could be understood using this example, that a coffee shop owner, suppose, wants to estimate the average amount of money the customer spent on coffee in a week, and they wish to determine that the average is within rupees 5 with 90% confidence. So here margin of error that he is taking, that E is taking to be 5, plus minus 5 he is considering that. Now based on historical data, it is estimated that customer spending ranges from rupees 100 to rupees 200 per week, and the spending behavior follows approximately normal distribution. How many customers should they survey in order to achieve this level of confidence and accuracy in their estimate? Now the question comes is that how many customers should he sample? So for that, what is given to us? Let us first see. In this problem, what you are given is E is given to you as 5 over here, because that is within 5 rupees. Z alpha by 2, that is 0.05 over here, that would be 1.645, because it is 1 minus alpha is 0.90. So you can think of alpha by 2 as 0.05, and this value comes out as 1.645. Now the range basically in this case, range is from 100 to 200. So if it is 100 to 200, so the range would be 100, and you have to divide by 4, so that would be 25. So sigma in this case would be 25. So if you just substitute these values in the previous formula for the sample size, that is Z alpha by 2 whole square into sigma square, so sigma is 25 whole square divided by 5 square. So this would come out as approximately 68. So you can say that they should at least survey 68 customers in order to achieve this goal. So you can see that this is important, because many times we are stuck in like what should be the sample size, right? That is the question that we often encounter. So for such situations, we can use this method. Now likewise, so till now we have been looking at two-sided confidence interval. We have a lower bound and the upper bound, but in certain cases we might be interested in just one-sided intervals, that mu is less than something, that is an upper bound for that, and in this case we have a lower confidence bound. So the same thing is happening in these two. We are just, so the other side is not written over here, right? It is easy to see. Now we move on to our next theorem, which says that what will be the confidence interval for mu when sigma is unknown. Now in this case, sigma is unknown. If you can recall, whenever sigma is unknown, your sigma, that is standard deviation, is replaced by the sample variance, or the sample population variance. Sigma square is replaced by the sample variance. So in that case, your t distribution comes into picture. So that is why if you have a random sample coming from a normal population with mean mu and variance sigma square, which is unknown to us, then the 1 minus alpha 100% confidence interval for the population mean mu is x bar plus minus t alpha by 2 n minus 1 s by root n. So what is happening over here? Again, you have this as the point estimate, and this is the quantity that you are adding and subtracting on both the sides. So let us see how do we obtain the proof for this. So our second theorem is about the confidence interval for mu when sigma is unknown. So we know that in the last case, when we are sampling from normal distribution, what we had was that x bar minus mu sigma by root n was used, and it follows normal distribution. And if you can recall, we have said that repeatedly that if sigma is unknown, so I replace sigma by the corresponding sample standard deviation by this, and it follows t distribution with n minus 1 degrees of freedom. So in this case, basically we use z notation for this, and we can say this is t over here. Now we use this logic in order to obtain the proof for this. So before that, let me just make a small figure over here. Okay, so here in this case you would have t alpha by 2. So t distribution is always accompanied with alpha and the corresponding degrees of freedom also. And likewise here also you would have minus t alpha by 2 comma n minus 1. So if I look at this side, so it would be this region, and if I look at this side, so it would be this region, and in between this it would be 1 minus alpha. So this is alpha by 2 and this is alpha by 2. Now, if I want to write the probability, it would be minus t alpha by 2 n minus 1. Here t, you can say that this is your capital T, then this is less than t alpha by 2 n minus 1. This probability is 1 minus alpha. So basically this value over here, this is the t value having area, this if you see, this is the t value having an area alpha by 2 to the right of it with n minus 1 degrees of freedom. And similarly this side, on the left hand side, it would be alpha by 2 area to the left of it. Now if you focus on this, we can just simply substitute as we have done earlier also, minus t alpha by 2 n minus 1. So instead of t, what I can write x bar minus mu s by root n, and this one would be t alpha by 2 n minus 1, right? So if I simplify this interval over here, you can see that I can take s by root n to the other end. So here you have x bar minus mu, this one would be t alpha by 2 n minus 1 to s by root n, and I can find bit for mu. So x bar minus t alpha by 2 n minus 1 s by root n, x bar plus t alpha by 2 n minus 1 s by root n. So this is the interval that we obtain. So if you can recall, in the slide it is mentioned as x bar. I can write x bar plus minus t alpha by 2 n minus 1 s by root n, or you can write it in the form of an interval, that x bar minus t alpha by 2 n minus 1 s by root n to x bar plus t alpha by 2 n minus 1 s by root n. So this is how you obtain the interval for your confidence interval. So this is how you obtain the confidence interval for population mean when sigma is unknown to you. And that is why we refer to it as the t interval for the mean, because we are using the t distribution concept over here. Now again, x bar is a point estimate for mu. Fine. And you consider the entire thing, that would be an interval estimate. S by root n is the standard error. And finally, this is basically t alpha by 2, this portion over here, this is the margin of error. If this is the margin of error, basically it means that obviously the width of the interval would be half of that, right? Because width of the interval will be twice of t alpha by 2 n minus 1 s by root n. Suppose you want to estimate the average time people spend commuting to work in your city, and you collect data from a random sample of 51 commuters and find that the mean commute time is 25 minutes with a standard deviation of 6 minutes. Calculate a 95% confidence interval for the average commute time in your city. So let us see what is given to you and what is asked. You are given a random sample of 51 computers, so n is given to you 51, and the sample mean, that is 25, and standard deviation, that is s, is given to you as 6. And you have to find out the 95% confidence interval, that is t alpha by 2 n minus 1. So you can simply substitute these values. So let us see. So if you look at the example, so n is given to you as 51. The sample mean came out as 25 and s is given to you as 6. And if I look at the t value, t alpha by 2 at n minus 1, or I could say t, it is actually 0.025 at 50. N minus 1 would be 50. Degrees of freedom is 50. If you look at 50 degrees of freedom, add this 0.025 in the t table, basically you will find that this value is 2.009. So if you substitute the value, so it would be 25 plus minus 2.009 into s basically divided by root 51. And if you solve this, it's approximately comes out as 23.31 to 26.6. 0.69, right? So this is the interval estimate that you obtain. So one thing that you can see from here is that if you know the concept, then the solution is easy, right? You just have to substitute the values, and obviously here the data has been summarized and you are given the value of mean, sample mean and standard deviation. Obviously when you are working in real life data, with real life data, then in those cases you have to calculate the sample mean and standard deviation, and then you can substitute it over here for a single sample problem. So in the same way, we can consider this example. Suppose we have conducted a study on the acidity levels of 61 soil samples collected from a particular agricultural region. The sample mean acidity level is 5.8 pH units and the sample standard deviation is 0.6 pH units. Now you have to calculate the 95% confidence interval for the mean acidity level in the soil of this agricultural region, and you also have to calculate the same thing for 99% confidence interval. So we are basically trying to compare what happens to the width of the interval if I am changing the confidence level, because the rest of the setup is the same. So n is given to you as 61 sample size in the first line. Sample mean is given to you as 5.8, that is x bar, and 0.6 is given, that is s. 95%, 99%, so you know how to find out the corresponding t value. So it will be t alpha by 2 n minus 1. So you will be looking at 60 degrees of freedom for both of these values. So let us see how do we do that. So these are the given values. So if you look at the table, this value is actually 2 because alpha by 2 is there. So it will be 0.025, and the interval basically in this case would be 5.8, that is x bar, plus minus 2, that is the t value, into s by root n. And if you simplify this, it comes out as 5.646 to 5.954. So you can say that we are 95% confident that the mean acidity level in the soil is between these two pH values. Now if you look at the width of the interval, basically width of the interval is 0.308. So the width of the interval is 0.308 when you are considering the confidence level 95. Okay. So let me just cross check. Yes, for 95%. Next we will solve for 99%. The same values are there. The difference will come in this t value. Now the t values over here is 2.660. Again we perform the same steps. We are just simply substituting the values, and what you obtain over here is this interval. So you are 99% confident that the mean acidity level in the soil is between these two. So the width of the interval in this case comes out as 0.408. In the previous case, it was 0.308. So you see that as you are increasing the confidence level, the width of the interval is increasing. And width of the interval is increasing from when you are going from 95% to 99%. So the precision is also decreasing. So in order to have the correct precision also, as I mentioned earlier for the sample size thing also, so we need to have 95% is a better option for us. Likewise, if we want to determine the sample size as we have done for the z interval, so here we will be considering again this margin of error was this. So if I calculate n from here, t alpha by 2 n minus 1 whole square, s square by e square. So now if we have to determine the sample size in case of the t interval, then we know that e, that is the margin of error, is t alpha by 2 at n minus 1 degrees of freedom into s by root n. Right, so if you solve this for n, you will get that n is t alpha by 2 n minus 1 whole square s square over e square. If you can recall from the previous one, that what is the difference over here? That z alpha by 2 is replaced by this t alpha by 2 at n minus 1 degrees of freedom, and sigma, as it was known there, so we had sigma. Instead of that, if we have s in this case, rest of it is in the same way. So now if you look over here, s, we know that it can be approximated basically if you take range by 4, as we have discussed earlier also. Also note that here n is present in t alpha by 2 n minus 1 degrees of freedom also. You have to solve for n only. Now how to deal with this? In order to find the value of n, we have two methods. One is the crude method, which is basically you replace this t value by the corresponding z value, z alpha by 2, and you solve this, and it would be approximately the same sample size as you would have obtained for t, because we know that t distribution approaches your normal distribution, right? It is similar to your normal distribution. So in that case, you can simply approximate it and you will get the answer. The other method is that you can use the iteration process. You start with some random guess for your sample size, and when you know the sample size, for that you will calculate the t value, you will have the s and e square, you will get certain answer to that. Again, you will plug that new value, again that will be the new starting value. At that degree of freedom you will calculate, and you will keep on doing it until you see that the difference between the two sample sizes is very, very less, right? So once it saturates, you can consider that particular n as your sample size. So this is the basic method for finding for n. So we have seen till now that if you have to find out the confidence interval for the population mean, so you have two possibilities: either you know the sigma or you do not know sigma. When you know sigma, that is the standard deviation, you get the z interval. In the other case, you get the t interval. And how do we find the sample size in both the cases, that we have also seen.